Good morning, everybody. So yeah, so like I said, are there any questions, comments, concerns? Nice. What's due tonight? Assignment number 2. Like I said, the grades for assignment number 1 got posted on Blackboard this morning. Class average was like 71, so it's not so bad. Yeah.
I do have a question. You said last week that it was fairly likely the first test would be at the end of this week. Do you have an update for that?
See, what happened here was I totally forgot that I was supposed to do that. He reminded me, everyone look at him, he reminded me that, yeah, you guys are supposed to take an exam.
Oh, we doing that good?
No, we're not doing
Oh,
We
man.
don't need one. It's totally fine.
Yeah, I mean, you want an exam? I'll give you an exam.
I just want to know when it is. Never.
Whenever I write it, right?
Just a point.
See, the mistake is thinking that I have some sort of like master plan that's already like figured out, right, and scheduled.
Slipped up.
Just making this thing up as I go along, man. Yeah.
Man.
No, we're not done with it. We got to at least get through chapter 4 before we can take an exam. Probably chapter 5. What's that?
Exams are take-home, right?
Exams are take on, yeah. Now I'm doing a thing where like we all log into Zoom and I like stare at you while you take the test. Yeah. She took it. She cheats. All right. Do you have any complaining about class not starting yet? Maybe it'll take longer.
Okay. I'm going to class after this, so.
All right. So like I said, the grader is tough, so make sure you guys are actually showing your work, not just punching stuff into calculators on that Unit 2 assignment. It's due tonight. The Unit 3 assignment, I think the calendar says it's due on Monday, but I pushed it back to next Wednesday.
Is that 15?
What's that?
Is that 15?
Whatever Wednesday is, yeah. Let's use this. And then let's see, so we're going to finish. So yeah, so chapter 3 is going to be due on Wednesday. We're doing chapter 4 today and on Monday, which means that the Unit 4, like I said, is going to be due a week after we finish it. So it's likely the Unit 4 assignment won't be due until next Monday.
That's fine.
And so like Monday after next. So like I said, that's how we're going to keep things going with the assignments. Any questions about that? All right, so today we're going to start in chapter 4, and it's almost time to start actually designing some digital systems. In fact, we're going to sort of do that today.
Is this called digital systems?
What's that?
Is this called digital systems?
It's what called digital systems.
This chapter?
Class is called digital systems.
Oh,
No, the chapter is not called digital systems. The chapter is called Applications of Boolean Algebra.
Oh, so the same thing as yesterday.
But the first section of today's lecture is called Combinational Logic Design using a truth table. Ooh. That's a lot of words. Table. All right. So what we're going to start with is just an empty black box. It's got 3 inputs that we'll label A, B, and C. And it's got some output F that is itself a function of A, B, and C. And we have a design that goes on the other side.
Would we lose points if we don't add the little dots to our drawing?
What are you talking about?
He's talking about like the endpoints.
You like these dots?
Yeah.
I don't know, maybe. Not the grader. He wields with an iron fist, so you might. Alright. So. Boy, I lost my train of thought. Okay. Our specification that we're going to use to design this particular circuit is going to come from the truth table. So on the left-hand side, we've got our inputs A, B, and C. And we'll label out all 8 rows. And on the right-hand side, we'll just list what F is. And we'll say that f is equal to 0, 0, 0, 1, 1, 1, 1, 1. So we know what the outside looks like. We know what the truth table looks like. Now what we need to do is actually figure out what the logic gates look like on the inside. So how might we start that? What's that?
An expression.
Expression of what? Of our love for Boolean algebra?
Sure.
What kind of expression?
Boolean.
Okay, yeah, we need a Boolean expression, that's for sure. Should we get started? F, A, B, C.
Well, we trying to figure out what logic gate that is?
What's that?
Are we trying to figure out what logic gate that is? That it's an and or something?
Well, we're trying to figure out what we've got this truth table.
Yeah.
We need to take this truth table and derive a Boolean expression. So what do you think?
It's adding that.
What's that?
It has to be adding that. It's not multiplying.
Has to be adding? Well, there's no adding or multiplying in Boolean algebra. Anding or, yeah. What do you think? Somebody, what would your guess? Yeah, yeah.
Take every combination of A, B, and C where F is 1, and it's like so F is 1 when B and C are both 1 and A is 0.
Yeah.
So write that expression, so like not A and B and C, and do that for every input where F is 1.
Good. You're absolutely correct. So what we can do is we can sort of imagine or write out a Boolean expression for each row of the truth table. So, and we do it by noting which is 0 and which is 1. So here we have 0, 1, 1. We're going to translate that into A naught, B, and C, right? So anytime something is inverted, that's a 0. Anytime it's not inverted, that's a 1. Yeah? And we'll do that for all of the terms in which f is equal to 1. So that'll be A, B naught, C naught, A, B naught, C, A, B, C naught, and A, B, C. Does that make sense to everybody? So what form are we going to write our expression in?
Sum of products.
What's that?
Sum of products.
Yeah, you said it like you were sure. Yeah, sum of products. It's always going to be the answer, right? Except when it's not. So yeah, so we write these out in sum of products form. So f is equal to A naught B C, or A B naught C naught, or A B naught C, or A B C naught, or ABC. Good. So now we have a Boolean expression. Are we done? We got to simplify, right? And last time, on Wednesday, we talked about a process for simplifying. And what was the first step of that process? Use the uniting theorem. Very good. The uniting theorem. All right. So where are some places up in here we can use the uniting theorem?
Use on the last two terms.
On the last two terms, A, B, C prime, or A, B, C? So let x equal what?
AB.
AB. And y is equal to
C.
C. Cool. Those guys are going to combine to be just for AB. Good. Where else can we use uniting theorem?
Second and third.
The second and third term. A, B naught, C naught, A, B naught, C. All right, what is our x?
AB naught.
B prime, and our y is equal to C. These guys will simplify to just A, B naught. All right, I'm going to write out our expression again. We got A prime, BC, or A and B prime, or A and B. Not so bad. Can we keep the uniting theorem train going? While they're thinking about that, Ethan asks on Discord, why would we not create expressions for the first three? And the first part of that answer is there are expressions for the first three. You know, 0, 0, 0 becomes A prime, B prime, C prime. 0, 0, 1 becomes A prime, B prime, C. And 0, 1, 0 becomes A prime, B, and C prime. We don't use them in our expression because we only use the terms for which f, the one that we're trying to design, for which f is equal to 1. And in this example, the first three are 0, so we don't use them. What you got?
Could you use them and then not your answer, convert your answer?
Ooh, yeah, we're gonna get to that. All right, well, let's finish this one first.
Oh, the last two terms.
Yeah. So the last two terms are pretty textbook uniting theorem, right? What does it simplify to?
Okay.
So we got f is equal to A naught B C or A. All right. One more thing we can do with this expression. Which theorem can we apply?
I don't know which one it's called, but
There's four of them. Uniting theorem. What's number 2?
absorption.
Absorption theorem. Number 3.
Elimination.
Elimination theorem. Number 4.
Consensus.
Consensus theorem. So which one are we going to use here?
Elimination.
Elimination. Elimination is the one that says what? What's its definition?
X plus X, or X or X not Y equals that X or Y.
Good. X or X prime and Y is equal to X or Y. Can we use that here?
Yeah.
You bet. What's our X?
A.
Good. So that means we're going to get what? A or BC. Is there anything we can do to simplify this guy further? No. It's good to go. All right. So first thing, any questions about how we did the simplification? What you got?
I'm assuming we won't be allowed to just, like, if we have a really simple one like this, just freehand the answers because you can get A or B and C just by looking at that.
Yeah, you can right now, but why is that not a good idea?
Well, obviously you won't be able to do it for advanced stuff.
That's what I mean,
If
yeah.
you were just writing out an answer on something, would we be allowed to just write the answer down instead of going through the process?
No, you gotta do the process. The whole point is the process.
Fair enough.
Because you gotta practice the process so that when we get to terms of like 6, 8, 16 variables, we know the process. All right? Don't cheat yourself and skip out on practicing the process while it's easy. You know what I mean? Yeah, so yes, you gotta do the process. Process is the point. All right, any other questions? All right, so the last thing to do is just draw it, right? I mean, also this is a really simple, even this one with 3 variables is pretty simple because it's all just, you know, this bank of ones. Yeah. When it's an easy one, look at it as an opportunity to practice the techniques. Because you'll need them when they come along later. So the last thing to do is draw the logic diagram. And this one's pretty easy. What do we got? We got a B, we got a C, we're going to feed an AND gate, which is going to get us B and C. Then we're going to feed an OR gate with A. And the last thing is F. And there we go. That's our whole circle of life there, right? We had a blank box. We were given a truth table. We used the truth table to derive a raw Boolean expression. We simplified it algebraically using the techniques that we knew. And then finally we designed the circuit. The rest of this class will basically just be that in an ever increasingly complex cycle. So, what's the process? We take the truth table, we derive a Boolean expression, we simplify that Boolean expression, we draw the logic diagram. We build it, we ship it, we make money. Yeah? Yeah. All right. So, any questions about this example before we move on? So, as was alluded to a moment ago, what can we do with the zeros? If the ones represent the definition for F, what do the zeros represent?
F inverse.
What's that?
F inverse.
F inverse, right? So we can also say that F prime is equal to what? What's that?
Sorry.
Skipping ahead?
Yeah.
Yeah. What do we start with?
A not B not C not.
Exactly, we do the exact same process for the inverse. In fact, we could even write out a truth table entry for the inverse and say F prime is equal to 1, 1, 1, 0, 0, 0, 0, 0, right? And then from there, the process is exactly the same as what we just did. So we lay it out, we got A prime, B prime, C prime. Or A prime, B prime, C, or A prime, B, C prime. All right, can we simplify this? How?
Uniting Theorem.
Okay, on what?
First two.
First two, right? So that's going to simplify to what?
A not B not.
A naught B naught. So A naught B naught or A prime B C prime. Is there anything else we can do with this guy? Simplify it a little farther, couldn't we? What do you got?
Can we factor in the A naught?
Come on, man. Yeah, we can factor out the A naught. Be left with B prime or B and C prime. B prime or B and C prime is an example of what theorem?
Elimination.
The elimination theorem. So that's going to simplify to what?
B
B prime to C.
Yeah, B prime or C prime. And then we distribute back. F prime is equal to A prime B or A prime C prime. So that's about as far as we can simplify f prime. But we're not done with the problem yet, are we?
Oh, the question on the second line says is x is b prime and then the bc is like x prime times y. Why is c prime?
What do you mean it just is?
Other than
Why is-
the-
why is
that's what I'm
B
saying,
prime? Why is B not
plus
prime?
X part, that's what I'm confused on. Why
I'm not
is
confused.
no-
Oh, you're right. All right, good catch. All right. So back to the question. We can't simplify it any farther. What do we do now? Is this our solution?
For F integers.
What's that?
For F integers.
Not for f, it isn't. Right? Because what is this?
That's F integers.
That's f prime. That's the inverse of f. Right? Remember, our whole goal is to design f. So what is the last thing we have to do?
Inverse it.
We gotta inverse it, yeah. So we take this and say f is equal to f prime is equal to a prime and b prime or a prime and c prime. Prime is gonna give us what? Good. A and B or A and C. So if we're going to draw that guy, we'll have what? A and B. One note about my own personal notation, if we're crossing lines, so for example, A feeds to both of these guys, when I draw it, if two lines cross and they're connected, I'll draw in the dot, I'll draw in the node, right? And if they're not connected, I'll just cross them. A lot of people do like that business where they draw this thing hopping the line. I think that looks dumb, so I don't do it. But you can do it, and that's just fine. All right. So here we go. A simplified, valid solution to our problem. Which one's better? What's that?
Well,
Yeah, this one, right? It's got less gates. Now, is there any way to know which one would be better before we did it? Not really.
The number of, is it like who has more? Or is it just two?
Yeah, right. So I mean, at the end of the day, right, we care about doing the same thing for less money, right? Less money means less logic gates. This required only 2 gates. That design required 3 gates. And they're both pretty simple, but one is demonstrably better than the other one. So if we were actually going to build it, we go with this one. All right. What's that?
Is there a way to look at the truth table and be able to see which one's gonna end
No.
up? Or you just
All right, you got it. All right. So because we're going to follow this process sort of over and over again, and we're even going to introduce some techniques that don't require Boolean algebra to simplify, we need kind of a shorthand notation for all these things. So we're not writing so much all the time. Which takes us to the second half of today's lecture. A thing called Minterm and Maxterm expansion. So let's do there. Minterm and Maxterm expansion. Now, so to put this truth table back up here, go ahead and do a free variable again. A, B, C. 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, no, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now the first thing we can do is we can label the rows, right? So we say row number. And we just count down. 0, 1, 2, 3, 4, 5, 6, and 7. 0, 1, 2, 3, 4, 5, 6, and 7. Of course, for a 4 variable, we go down to 15, so on and so forth. Now, simply put, the minterms are those product of sum of products terms that we did initially when we did this first example, right? So for this first one, we would say little m 0 is equal to a prime, b prime, c prime. Little m 1 is equal to a prime, b prime, c, and so on and so forth. Little m 2 is equal to a prime, b, c prime. Little m 3 is equal to a prime, b, c. 4 is equal to a, b prime, c prime. Little m 5 is equal to a, b prime, c. 6 is equal to a prime. Wait. Let's read the last one. No. A, B, C prime, and 7 is A, B, C. So basically, instead of writing the Boolean variables, we'll just list which term it was. So let me do this real fast. The function that we had before in our first example, 0, 0, 0, 1, 1, 1, 1, 1. So what we would do, instead of writing that big, long mess of an expression, is we could shorthand it. We could say that f, the function of a, b, and c is equal to just m3, or m4, or m5, or m6, or m7. Now let's see what we've done. And we can shorten it even farther by using the thing that we're going to keep using, which is this. We're going to write capital sigma for sum, the sum of minterms 3, 4, 5, 6, and 7. Yes?
And then the m's are lowercase or uppercase?
The lowercase. Yeah, okay. Cool. Any questions about that? Yeah, so instead of writing on that big long Boolean algebra, that's what we want. And a lot of our non-algebraic optimization techniques will start with just having this expression, which is a lot easier to derive. Now, let's do a thing before we talk about the Maxterms. I probably should have done before. Let's go back and revisit real quick that f prime. I'll write it out again. Remember we said f prime was equal to a prime, b prime, c prime, or A prime B prime C or A prime B C prime, right? Now, if we just right off the bat took the inverse of this, what would we get? We said let's invert all of that without doing any simplification. What would our F be?
A or B or C and A or B or C naught and A or B naught and C or C.
A or B or C prime and A or B prime or C. So, F is equal to this big long expression. These are the max terms. Right? When we take the inverse, when we consider the place on the truth table where F is equal to 0 and do it in product of sums instead of sum of products, that's what the max terms are. So we would say big M0 is equal to A or B or C. And then big M1 is equal to A or B or C prime. Big M2, I'm going to list all these out, A or B prime or C. Big M3 is equal to A or B prime or C prime. Big M4 is equal to A prime or B or C. Big M5 is equal to A prime or B or C prime. Big M6 is equal to A prime or B prime or C. And then finally, big M7 is equal to A prime or B prime or C prime. These are the max terms. So, instead of listing out the Boolean algebra, we would say that F is equal to big M1 and big M2 and big M3.
Must be 0 and 2.
Oh, yeah, so that. Let's read up my notes too when I wrote down. 0, 1, 2. Or, just like how we simplified it up here to this generalized expression for the max terms, we will say that F is equal to, use capital pi for product, a big M, capital M, of 0, 1, and 2. Any questions about that?
Interesting.
I think so. All right. Let's do a couple quick examples. Let's see. Everybody got this down?
Wait, what's the thing on the bottom?
What's that?
The thing on the bottom, I do, so I guess I wasn't paying attention right now. What's that thing at the bottom?
What is this thing?
Yeah.
It's the signifies, remember we talked about ands as like their multiplications, right? So M0 or M1 or M2, we just write it simply as the product, right? Capital pi stands for multiplication. In this case it stands for and, the product of max terms, 0, 1, and 2.
Oh.
So now, instead of doing a bunch of stuff, what if I said 0, 1, 1, 0, 0, 0, 1. And I asked you, what is the generalized Minterm expansion, that thing that involves sigma, of F? We said F is a function for the sum of minterms. Which ones?
1, 2, 6.
Hmm?
1, 2, 6.
1, 2, and 6, good. And if it's a sum of minterms, 1, 2, and 6, that means it's a product of max terms. Which ones? Remember that minterms are all the ones, max terms are all the zeros.
1, 4, 5.
What's that?
And 1, and 0.
Yeah.
And 3 and 4 and 5.
Yeah, 0, 3, 4, 5, and 7. Also, sometimes beneficial to list out the complements in this way. So if I say that f prime is also a function of a, b, and c, what is this generalized minterm expansion? Don't overthink.
Just the midterms for 0, right?
What's that?
Just the midterms for 0, right?
That, yeah. What is that prime equal to?
Just the sum of 0 through 4, 5.
Wait, say it again?
The sum of the little m for the same number, 0, 3, 4, 5, and 7.
Gotcha, yeah. Sum of minterms 0, 3, 4, 5, and 7. Which means the product of which max terms?
1, 2, and 6.
1, 2, and 6, good. Perfect. So that's what you need to be able to do, is look at the truth table and basically come out for all 4 of these things. What is f as a sum of minterms? What is f as a product of max terms? What is f prime as a sum of minterms? And what is f prime as a product of max terms? And it's pretty easy, right? This is where the 1s are. Product of max terms is where the zeros are. For f prime, the sum of minterms is where the zeros are. And for f prime, the sum of the product of max terms is where the 1s are. Any questions about that? Cool. Any questions about anything we talked about today? What you got?
What exactly midterm and maximum? I'm kind of confused with everything.
What do you mean?
I was just like, what are they like supposed to represent? I'm so confused about it.
That's a loaded question, man. So they are a shorthand notation for all of those Boolean expressions that we used in our first example. You know how we wrote out a big long Boolean expression? Right? We don't want to do that. Instead, we want to just write this because it's quick and easy. Yeah? So all it is just a shorthand, right? M0, or minterm 0, just means A naught, B naught, C naught. Right? And max term 1 is just A or B or C naught.
And if we wanted to simplify it, we would just like put it in the big form and simplify the big form.
Yeah. And as I was talking about, we're going to work on some techniques next week where we just look at this and simplify without doing any Boolean.
Basically just simplification.
What's that?
It's basically just just a simplification.
Yep.
Or you can just put ML and 1 and 2 instead of putting all those knots and A's, B and C.
Yep, it's just a shorthand to speed things up for us. All right, anything else? What you got?
So does like the number of minterms and maxterms like help you like give insight into like, cause you know how when we were doing like the sum of products and the product of sums and
Mhm.
the logic gates after that? Does the number of terms in the minterm and maxterm give insight into which will be more efficient, like use less logic gates?
So the question was, does the number, simply the amount of midterms and max terms give us some insight into which will be more efficient?
Yeah.
Yes-ish. What will be more important is the relationship between the numbers. Does that make sense?
Yeah.
So for example, we get, if the midterms are all powers of 2, right, that's going to mean something, and stuff like that. So it's not so much the count of the numbers, but what is the relationship between the numbers that appear? That's going to matter. Cool? All right. If there's nothing else, have a good week and be safe. Don't forget that Unit 2 is due tonight at midnight. And I'll see you guys on Monday.
Will you talk about our grades?
What's that?
Will you talk about our grades, like what we got wrong, or is it uploaded to the Blackboard, or how?